Okay, good day. This is Pre-Calculus. I am Mr. McCully, and this is the presentation for Lesson 43, Counting Principles. Let's get right to it. So today we're going to talk about counting principles, and we're going to solve some simple counting problems involving the fundamental counting principle. We're going to use permutations and combinations to solve counting problems, and we are going to describe the distinguishable permutations in a set. So let's talk about some of the definitions of these things. First, the fundamental counting principle. Let E1 and E2 be two events. E1 can occur in M1 different ways, and E2 can occur in M2 different ways. The number of ways those two events can occur together is M1 times M2. And so that's a fairly complex way, excuse me, to explain something that's actually fairly simple. Let's talk about this example here. If you have 5 shirts and 4 pairs of pants, how many different outfits could you create? Well, the first event, E1, is to pick a shirt. The second event, E2, is to pick a pair of pants. And so the number of ways that you can pick a shirt is 5, and the number of ways that you can pick a pair of pants is 4. So the number of different outfits that you could create is just the multiplication of those two ways. So 4 times 5 gives you 20. Now, if you extended that and said, all right, let's say I had 3 different pairs of shoes and I wanted to include that in the mix. Well, that would be a third event, and so it would be E3, and it would have a third number of ways that you could do it. M3 would be 3, and we just go 5 times 4 times 3 is 60. Very similar. Next, permutation. The permutation of n different elements is an ordering of elements such that one element is the first, one element is the second, one element is the third, and so on. And so in that particular instance, order is important, all right? So the number of permutations when you're, I don't know why it keeps doing that. The number of permutations of n elements is just going to be n factorial. So if I take all of the elements and I want to order all of the elements, it's just that number of elements factorial. That's what that exclamation point means, and we've talked about that before. If you're choosing only some of the elements out of that group, then you can use NPR. All right, now NPR is, let's say you had 5 elements and you want to order 3 of them. Well, that would be 5 elements ordered 3 at a time. All right, and so you have n factorial over n minus r factorial. And this calculation is in the calculator, so you don't necessarily have to memorize this equation. So I'll only ask you to use the calculator to find it. Combinations has a similar equation, but it's a little bit different. And combinations, we're going to find out on the next page, talks about when order is unimportant. So just as a for instance, let's say I had 3 ping pong balls with the letter A, B, and C on them. And then we drew them again, and I got C, B, A. And then I drew them again, I got B, A, C. And I drew them than that. If we're talking permutations, this is 3 occurrences. If it's combinations, this is only 1 occurrence. Because in permutations, the order at which they come out is important. But with combinations, it's just having those elements. As long as you have those elements, you're going to get it. That will only count as 1. And so to define that formally, in combinations, it's the number of ways items can be chosen from a group when order is not important. In permutations, it's the number of ways items can be chosen from a group where order is important. And again, so just to reiterate, permutations, you're always going, or I can't say always, in almost every case, you're going to have more than if you did combinations. So if you did 5p3, that number is going to be bigger than nc3 or 5c3. Next, distinguishable permutation. So suppose a set of n objects has n1 of one kind, n2 of a second kind, and n3 of a third kind, and so on, so that if I add up the total numbers of each indistinguishable kind, it matches the total number of elements. Then the number of distinguishable permutations is at n factorial, so we're counting all of the um, possible orderings that you could have. And then we're going to reduce that by dividing by each of the number of similar elements factorial. And I'll have an example of what that means later here in the examples. But let's start with some simple examples. Let's say we have a computer program that generates a random number from 1 to 20. Determine the number of ways a number can be generated that's a number larger than 15. Well, if I'm only generating from 1 to 20, 16 is bigger than 15, 17 is bigger than 15, 18 is bigger than 15, 19 is larger than 15, and 20 is larger than 15. So 1, 2, 3, 4, 5, there are 5 ways. All right. The number of ways you can get an odd number. Well, 1's an odd number. 2 is not an odd number. Come on, get with it, Macaulay. 3's an odd number. 5's an odd number. 7's an odd number. 9's an odd number. 11, 13, 15, 17, and 19. I don't think I missed them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different ways. All right. A pair of integers whose sum is less than 5. So if I'm generating 2 from that 1 to 20, 1 for the first one and 1 for the second one, well, that would be 2, so that's less than 5. 1 and then a 2, well, that would be less than 5. 1 and then a 3, well, that's 4, that's still less than 5. But if I go 1 and a 4, that's equal to 5, so that wouldn't count. I could generate a 2 and then a 1. That would be less than 5. That's only 3. I could generate a 2 and a 2. That's 4. That's less than 5. But if I go 2 and a 3, that's not. 2 and a 3 is 5, so we wouldn't count that. And then I could go 3 and a 1. All right, 3 and a 1 would be 4. That's less than 5. Any other generation of two numbers from 1 to 20 is going to generate a sum that's 5 or bigger. So I have 1, 2, 3, 4, 5, 6 different ways that I could generate a pair of integers whose sum is less than 5. Another example, Professor McCulley is getting his teaching schedules. If he is assigned one level of each of 3 levels of statistics, 5 levels of calculus, and 4 levels of algebra, how many different schedules could he have? All right, so I have 3 different things that I have to teach. I have 3 ways that I could teach a statistics class. I have 5 different calculus classes I could choose from, and I have 4 different algebra classes. So 5 times 4 is 20, 20 times 3 is 60 different schedules. Right. Let's move on. Okay. Example, a car license on Macaulaytopia is comprised of a set of 3 letters and 4 numbers, the first of which cannot be 0. How many license plates can be made using this system? Okay, so I can have 3 letters. So let's kind of draw this out, and this isn't the way that you would normally do it, but I have 3 letters. I have 4 numbers. RS, come on, Macaulay. And then this one can't be 0. All right, so if I could pick any letter for any of these, there's 26 different letters. So there's 26 for each, and we'll say each of these is an event. We choose the first letter, the second letter, the third letter. And so the simple counting principle says that for the letters, I'm just going to multiply those things together. And then for the numbers, well, it can't be 0. So if I can't choose 0, then I have 9 different numbers for the starting one. And then I could have a 0 for the other ones. So I'll have 10s for each of those. So if I want to calculate the total number of license plates, I'm going to multiply all of these things together. So I'm going to grab my graphic calculator, and 26 times itself 3 times is just 26 to the third. And then we want to multiply that by 9. And then we want to multiply that by 10 times 10 times 10, or 10 to the third. We multiply that together, and that's a pretty darn big number. So 1581, 1581, 84, and then three zeros. 8430. So 158 million license plates. LICENSE plates. That's a lot. A lot of cars. Okay. Next, example, use your graphing calculator to evaluate the following. So 5 chosen 3. So these are 5 permutations of 5 objects chosen 3 at a time. So let's see how we do that in the calculator. Now, when you want to do permutations or combinations, you're going to put that first number first. That's just the way that you're going to order it. You're going to hit the math button to bring up this tab of different things. We're going to go over to the probability tab of this menu, and you'll notice there's my permutations, there's my combinations, and there's my factorial. So we're going to go to there, and you'll notice that 5 went down into the lowercase where the n should be, and so p, and then I need to put a 3 there for that last one, and we get 60. And so that's 60 different values. The next one, 4 fathers have 2 daughters each, and they are all going to see Frozen at the movie theater. How many ways can the 12 people be arranged if A, there are no restrictions? Well, if I am arranging, that means order is going to be important. And so it could be either 12 factorial, that works because I'm choosing all 12, or you could go 12p12. Using permutations where you're choosing all of the items also works. And I'm going to do it that way simply because I already have this up, and if I go second and then I go entry, that brings that back up for me, and all I have to do is change the numbers, and then I don't have to mess around with the different menus and tabs. So choose 12, and that's a pretty big number. So let's see here. It's 4, 7, 9, 2 zeros, 16, and 2 zeros. So that'll be 4, 7, 9, 2 zeros, 16, and 2 zeros. So 4, 7, 9, 2 zeros, 16, and 2 zeros. Is that correct? 4, 7, 9, 2 zeros, 16, 2 zeros. 1, 2, 3. I've got, oh, that's a problem. I've got my comma in the wrong place. So 479,001,600 different seating, EATING arrangements, ARRANGEMENTS. I think so. All right. So if each family has to sit together, well, there are 4 families. So the 4 families can be arranged 4 factorial ways. The families can be arranged. And then, since there are 3 people in each family, 3 factorial ways the members of the family can be arranged. And so together, there are 4 factorial ways that the families can be arranged. And for each way that the family can be arranged, it has 3 factorial ways to arrange the members of the family. So let's grab our calculator. So 4, hit the math, go over to probability. We'll hit 4 for factorial, times 3, math, go over to probability, hit the 4 for factorial, and we get 144 seating arrangements. All right, and so what we can conclude from this is, notice that these things go up very fast as the number of items goes up. So if you only have 4 items, number of arrangements aren't very big, but the moment you start getting into that 10 or 12, those things start really, really jumping up there. Okay, last one. How many distinguishable ways can you order the letters in the word banana? Well, again, it's distinguishable. How can I tell the difference? So if I wrote B-A-N-A-N-A and said that I took these first 2 A's and I switched them, you wouldn't be able to tell the difference between those 2 two spellings. So these two are not distinguishable ordering. But if I arranged it so that it was in, say, alphabetical order, we go A, N, or excuse me, B, and then two N's. Well, I can tell the difference between that ordering and this ordering. So these two are two different distinguishable orderings. So we go back to that little, it's not really a formula, but it gives us an idea. The number of total items is going to be 6 because there are 6 letters. And then I have 3 repeated A's and 2 repeated N's. So if I want to make that calculation, there are 6 factorial ways that I can order 6 elements. Since there are 3 A's and 2 N's, all right, we're going to divide this by 3 factorial and 2 factorial. So if I grab my graphing calculator, we'll go alpha, we'll go y equals to bring up the fraction, we'll go 6, we'll hit math, we'll go over to probability, hit 4 for factorial, and then on the bottom, we'll go 3, hit math again, go over, hit 4 for factorial, times 2, go over to math, probability, 4 for factorial, hit enter, and we get 60 different orders. Well, that's all I got for today, folks. So the Star Wars fun fact of the day: the Mandalorian series makes use of stagecraft, which is this new technology made by Industrial Light and Magic, and so they're able to project virtual environments around the actors. So it's like a big circle, and then they project on a screen these environments, and then they just take the video of that, and very little physical objects were built. And if you look real close on this bottom one here, you'll notice that in the scenes where he had the ship, they only built the cockpit and then they projected the rest of the ship on the back of it and filmed it that way. And because film is only 1D, it has no depth, and you can't tell that this any depth perception in there. It all looks like one seamless picture. So it's pretty cool. And that's all I got for today, folks. Have a good day. Bye.